The ultimate goal of imaging is to create lenses which can look through any translucent obstacle. Lenses can be thought of as devices which reverses the effects of light propagation. Conventional lenses reverses phase changes as light propagates through vacuum. However, conventional lenses cannot restore phases of light propagating through more complex material. Moreover, conventional lenses cannot restore near fields that are localized near the object. Hence, it limits resolution. In contrast, perfect lenses restores both phase and amplitude, allowing unprecedented resolution. The principle of the perfect lens comes from the reflection symmetry in Maxwell's equations. Suppose if I have a translucent obstacle with a certain set of permittivity and permeability that I like to see through. Now if I have a second slab of material that is a mirror copy of the first, except all the eigenvalues are reversed in sign, then this second slab of material behaves as an optical antimatter to the first. In other words, this second slab of material is equivalent to a perfect lens. In practice, it's simple to find a material that is a mirror copy of the first, but it is difficult to find one in which the signs of the eigenvalues and eigenvalues are reversed in sign. It turns out that we can achieve this sign flip if we can reverse the frequency of light. Frequency reversal is also equivalent to spatial phase conjugation, a technique widely known and used by nonlinear optics community. Now, if we sandwich a mirror copy of our obstacle between two phase conjugate sheets, this new composite slab will be the required perfect lens. Unfortunately, phase conjugation not only reverses the frequency of light, it also changes the amplitude of light passing through the phase conjugate sheet. This distortion prevents the image formation. Fortunately, we can remove this distortion if we can add gain to the phase conjugate sheet, something which is not difficult to do in practice. Moreover, the gain that we add into the phase conjugate sheet can compensate losses from the obstacle, allowing us to see through even lossy obstacles such as fog or milk, something which cannot be done with conventional passive perfect lens. To demonstrate and illustrate what we have said, here is a numerical experiment. In the first setup, we have an object which looks like a double annulus. Now, if we place a lossy slab of obstacle, the image of the object would look like this. Clearly, we can no longer see the annulus at all. Now, if we have two phase conjugating sheets without mirror copy of the obstacle, that is, if we have the sign flip without the mirror copy, then the image of the object would look like this. Now we can see the annulus, but we cannot see the finer features. Finally, if we were to place a mirror copy of the obstacle between two phase conjugating sheets, satisfying all our criteria for the perfect lens, then the image of the object would look like this. Now we can clearly see the image of the object. In principle, the more gain we pump into the phase conjugating sheets, the better the resolution of the image. In conclusion, we have shown a systematic approach to design such perfect lenses. We call such lenses phase conjugate lens. Such design is a universal top-down approach tailored to any obstacle. Such phase conjugate lens can see through even lossy obstacles such as milk, fog, or even skin, going beyond conventional passive perfect lens. There are only two requirements in order to construct such lenses. First, we need a mirror copy of the obstacle, and second, enough gain in the phase conjugation sheets. Once satisfied, we should be able to construct such a perfect lens.